So another thing in this chapter is this idea of the average rate of change of a linear function. So we're going to kind of build two ideas together. We've seen the average rate of change, again, over some interval a to b. All right, that's basically our f of b minus f of a all over b minus a. Of course, that's also the difference quotient f of x plus h minus f of x over h. So that's how we're going to kind of approach this here. So if we don't have an interval like we don't have here, what we do turn to is the difference quotient, which is basically the same thing. What we commonly saw when we were doing the secant lines is that this also is just slope. So we're going to see that in action, and then I'll say some things, and we'll be able to do some more stuff as you see on the bottom. So for this first one, again, if we find f of x plus h, that would be 3 halves x plus h minus 1. So I get 3 halves x plus 3 halves h minus 1. So putting that in my difference quotient, right, I would have f of x plus h, so that's what we just found, 3 halves x plus 3 halves h minus 1, and we're going to subtract the function, which is 3 halves x minus 1, and this is all over h. So I just basically substituted those function values in. Distributing the minus, we get 3 halves x plus 3 halves h minus 1 minus 3 halves x plus 1. This is all over h. That cancels, and that cancels, and that cancels, and that cancels. So what's left is 3 halves h over h, which equals 3 halves, which we identified as our slope earlier. So that kind of solidifies what the difference quotient and what the average rate of change is. It's basically the slope, right, over an interval, or the slope of a function, right, over any interval that we can imagine. So again, if we use the difference quotient here, we know the slope is -4, so I'm anticipating -4. So what is f of x plus h for this example? Well, that's -4 times x plus h minus 3, which becomes -4 minus 4h minus 3. So putting that in the difference quotient, we have -4x minus 4h minus 3. We're going to subtract the function, which is -4x plus 3, and that's all over h. So dropping the parentheses and distributing the negative, we get that. The x's cancel out, the 3's cancel out, and -4h over h leaves us with -4, just as we expected. And even this guy here, we know the slope is to be 0, and f of x plus h is also equal to 2, right? This is basically a constant function, so it doesn't matter how far, any value that I put into the function is equal to 2. So putting this in my difference quotient, I have 2 minus 2 all over h, which is 0 over h, which gives us 0. Okay, so we know then that the average rate of change is constant. It's the same, right? And so that means that the change in y over the change in x is equal to some constant number. The change in y will be some constant number divided by some change of x. That'll be a constant number, which will give us our slope. Okay? And that can help us looking at a table of data. All right? When I look at a table of data, what we can basically determine is what's the change of x and what's the change in y. And if these two numbers are constant, that means that that ratio is going to be constant, which means that this data set represents a line. And then we can find equations of lines and all that other good stuff from the data that's given. So in this case, if we look up, right, we're going from -4 to -2, so that's a step of 2. From -2 to 0, that's another step of 2. From 0 to 2, that's another step of 2. And from 2 to 4, that's another step of 2. So it looks like as we run through the x data, the change in x is constantly equal to 2. So far, so good. Change in y, well, when we go to -7 to -4, that's a +3, another +3, another +3, and another +3. So the change in y is +3. So that's also constant. So that means that the slope is constantly equal to 3 halves. So this is linear data. All right, we can find the equation of that line and do all the stuff we did way back when we did that. So that is a linear equation, and again, I'm kind of tail doving that on the fact that we expected, right, the average rate of change to be constant. So if I observe that constantness, if you would, in the table, that must mean I'm a line. So the next one, when I go from -8 to 3, that's a step of 5. When I go from -3 to 2, that's also a step of 5. 2 to 7 is a step of 5, and 7 to 2 is a step of 5. So far, so good, right? Our delta x is 5. What about y? Well, 4 to 2 is a drop of -2. 2 to 0 is a drop of -2. 0 to -2 is a drop to -2. And -2 to -4 is a drop of 2. So we're constantly subtracting 2 from each guy. And so that means our change in y is -2. And it's also constant. So that means our slope is -2 over 5, which means that this is also representing a line. So we can find the equation of that line, do all that good stuff that we did way back when, and find the function that fits that data. Okay? Next table, it looks like we're going by a step of 3, a step of 3, a step of 3, and a step of 3. So delta x is 3. Here, we're constantly equal to 4. So at each step, right, the change in y is 0. So my slope is 0 over 4, which means my slope is 0. So this is also a line. We also know it's horizontal, right? That's an easy equation to find, right? Y, since we're talking functions, f of x equals -4, right, would be the line that fits that. Okay, so far so good. Everything seems linear. So the next step, we have a change in 3, a change in 3, a change in 3, and a change in 3. So in this data set, delta x is 3. So far so good. -10 to 0 is a step of 10. 0 to 4 is a step of 4. So I already know that this is not a line. I don't even need to go any further, because as soon as we find a change in y that's not constant, we're done. But you know, if we had to, notice how this thing is constantly changing, right? We have a step of 10, a step of 4. We're actually dropping down 2 and then dropping down 8. So there's nothing consistent about this at all. So right, that means that this is not linear data. So that is how we can tell whether a line or a table of data is linear. And of course, once we find out that it's linear, we can find that equation of a line. And I'll let you guys remember how to do all that from way back when in 2.2. Alrighty, so that kind of covers up this idea where we related the average rate of change or our difference quotient to our linear function. So much more to do. That's coming up soon in another video.